So I want to talk briefly about how cladograms and shared characteristics can really show some powerful information about how organisms evolve. Here what we're looking at is several different reptiles. We have three modern reptiles, so turtles, snakes, and lizards. All of these fall into the category of reptile, which is one of our vertebrate categories. The remaining three are no longer living. These are extinct reptiles. So these are the ancestors of some of the modern reptiles that we're used to. I'm going to start all the way down the bottom here. This is 320 MYA, which stands for million years ago. There lived what we believe is the earliest known reptile. And you'll notice that it looks very similar to lizards. It has a head and four legs, this long tail. The legs are out to the side, like modern reptiles. And not a lot has changed in 320 million years, to be honest. This body works. Natural selection caused this body to be successful, and sure enough, 300 million years later, we still have organisms that look very, very similar. However, like you've learned in the previous unit about natural selection and evolution, it wasn't the perfect body shape. There was always some that were a little bit better at surviving and reproducing, and so there's slight differences. So let's sort of fast forward in time a little bit. One of the organisms that evolved out of this early lizard was basically just another lizard. Same sort of shape. Again, the legs out to the side, the long tail, not a lot has changed. However, a different group of lizards, this is recently discovered, had these really weird looking ribs. Their ribs were really wide. They sort of formed a bony shell around the body of the lizard. So you notice not a lot has changed. In 80 million years, again, the lizard still has the head, the legs out to the side, a tail. It has many of these same characteristics. Now, because this lizard had these sort of large bony ribs, given enough time, 240 million years, that was chosen by natural selection to be sort of really advantageous. And so over 240 million years, lizards that looked like this, the population slowly changed and the traits changed so that lizards like this, instead of having these ribs that were quite wide and protected the body, eventually turned into the turtles we know today. So if we go back, we can sort of see those changes. Turtles still have heads and legs and tails, just like their ancestors long ago. They have that shared characteristic. But through natural selection and evolution, some of these traits we can see in past versions in their ancestors. 240 million years ago, there was a lizard with kind of a turtle shell, or at least the beginnings of it. Given enough time and enough selection, pressure, turtles evolved. But let's go the other way. The other way we go, and the populations of lizards really remain largely unchanged. The body structure worked. So how do we get these last two groups? Well, again, it doesn't take a huge stretch of the imagination to really see what's happening here. The first group that we can see split off is snakes. Now, this might feel like a stretch, but really, snakes and lizards are not that different. If I could take an eraser and just erase the legs off of a lizard, well, wouldn't I just have a snake? They both have heads, they sort of long bodies, long tails. And in fact, snakes did evolve from these early sort of lizard creatures 300 million years ago. Now, they didn't just have their legs fall off, but due to natural selection, and we're not 100% sure why here, there are some different theories about it, the legs became less important based on where these early snakes, so somewhere in here, again, this arrow is representing sort of evolution over time. Over 300 million years, the ancestors of snakes, their legs weren't advantageous. Snakes with smaller legs did better. Eventually, those legs got smaller and smaller and smaller until, sure enough, you end up with snakes with no legs. Although in a really interesting twist, every once in a while, snakes are born with sort of odd mutations that add legs back on. In fact, their genes of snakes just turn off the legs. So with a mutation, you can actually get snakes with the legs turned back on, And how is that possible? Well, because the genes for legs exist because they came from an ancestor with legs. But that obviously doesn't explain how we have reptiles like today. So here's the last branch. You'll notice modern reptiles are really unchanged over 320 million years. This body works well. This is a very effective body shape. So natural selection would not really change much. There was no reason, there was no selection pressure to change this body shape. And so, sure enough, modern lizards look almost identical to their ancient ancestors. So that shows how things have changed. However, this also shows some other interesting relationships between these organisms. So for example, a snake and a lizard are closer related than a snake and a turtle. A snake and a lizard are more closely related than a lizard and a turtle, because these two groups share a common ancestor that is more recent than the turtle. In fact, to find the ancestor of turtles, snakes, and lizards, we need to go back 320 million years. More recently, snakes and lizards had an ancestor. So we can see that these two groups are more closely related. They have more shared characteristics than either of these groups do with the turtles. And that's the power of the cladogram, of these sort of evolutionary trees, is that we can see and we can speculate how evolution occurred, and we can also see how organisms that look very dissimilar can actually be related, and how ones that maybe we wouldn't think would be related indeed are.